Chapter 8, Image Post-Processing and Volume Rendering. Nearly all images produced in a radiology department are processed to at least some extent. Some processing is utilized to bring out certain features like bone and soft tissue kernels in CT, or to provide a higher resolution like in MRA. These types of processing are done to primarily make the images more visually pleasing, but another use for post-processing is to improve the performance of the CAD algorithms, like I mentioned with the mammography exams. So we'll start with some image filtering techniques. A histogram manipulation is when you use window and level manipulation. There's an indirect relationship between window width and contrast. Enhancement. Under this category, there are two different filters. There is unsharp mask filters, which are applied to images to bring out features of detail, and edge sharpening filters, which enhance edges in an image based on the edge strength of the image. Moving on to another type of filtering, frequency filtering. This uses a Fourier transform, which converts an image from spatial domain to a frequency domain. And I'm just going to point out the picture right here in the top right. So the difference in these two images right here are that the one on the right has an edge sharpening technique enhanced into the image. The first image has low contrast in some critical areas of the image. You can see in the lung base right here. And also, if you look at this button, that was an artifact on the image, it does not have the unsharp mask filter applied right here. However, by applying the unsharp filter, it balances out the contrast and also makes the image appear sharper, which allows the radiologist to see the nodule that is down in the circled area much clearer. And then you can also look at the button. In the first image, you cannot even see the holes that are in the button, but if you take a look over here, much sharper image, much more detail. Noise are random fluctuations in the image formation that can obscure the true elements in the image, and noise is present in all images. Noise reduction is also called improving the signal-to-noise ratio. We can reduce noise by increasing the radiation in general X-ray or by doing some other things. So, example, we can increase the field strength or imaging time in MRI. Image processing does allow us to reduce the amount of noise on an image, but sometimes it increases the artifacts, so not always a great trade-off. We are going to discuss 3 different types of filtering in relation to noise reduction. Remember, filtering is a processing method, and it enhances or removes a specific component in a signal or in an image. The first one we will talk about is averaging, which is also known as block filtering. This is where each pixel is replaced by the average of its neighbors. So this is also the simplest filter for noise reduction. Then there is medium filtering. In medium filtering, the filter considers a patch of the neighboring pixels around a certain pixel. And the intensities in the patch are sorted, and the median value is chosen in the output pixel. This is a simple and efficient noise reduction filter. Then there is the non-local means filter, which is a newer technique that examines a patch centered about each pixel. The output pixel is a weighted average of center pixels from patches in a user-specified search region. Patches of the similar contrast and intensity are more heavily weighted in the non-local means filter technique. The idea behind the non-local means is that the similar patches will wash out the noise when averaged. Patch size and search region influence the quality of results and the processing time. Segmentation is the separation of an image into meaningful components. This usually refers to a certain anatomic structure or disease process. Global thresholding is where a pixel is considered foreground if its intensity is higher than the threshold value, and background if it is lower. This is the most basic and fundamental segmentation algorithm. Then there's classification, which is the assignment of a meaningful name to a group of pixels or values. So this picture right here is just an example of liver segmentation using the thresholding technique. So figure 8.6 in your book also gives an example, so I'd like you to take a look at that as well. If you've ever done any angiography 3D reconstruction with CT studies, you're performing thresholding when you remove bone from the images. Oftentimes the contrast materials and the calcifications you will find will still be included in the images when thresholding is applied because it looks similar to bone in the computer's eyes. Registration. This is the process of aligning images with one another. Algorithms are used to determine if images are in alignment. The purpose of registration is to geometrically align one image to another so that voxels representing the same underlying structure can be superimposed. This means that basically the same tissue samples that lie at a given XYZ location will lie like that on all of the registered images. It can deal with images from one modality, or it can deal with images from more than one modality. In medical imaging, 3D volume data are used in a rectangular format grid consisting of multiple slices, where each slice has a dimension of 512 by 512 or 256 by 256. Volume rendering is a visualization technique to display a 2D image of a 3D image dataset that retains access to the original voxel data. It is often referred to as 3D reconstruction. Projection rendering is the simplest and fastest volume rendering method. Maximum intensity projection, or a MIP, is a common example. MIPs are commonly used but do not have depth information, which may obscure important structures. Shaded surface display. This extracts the surface of certain objects and then renders it. Direct volume rendering renders images of 3D volume sets directly from the 3D volume data without extracting any geometrical information about the objects captured. So going back real quick to shaded surface display, I just want you to know that this can be fast, but it really doesn't provide any view inside the object that we're looking at and requires segmentation that is kind of labor intensive sometimes. Multiplanar reconstruction is the reconstruction of images in arbitrary orientations such as orthogonal, oblique, or even a curved plane. In multiplanar reconstruction, a volume is built by essentially stacking all the slices, and then the software cuts through the stacked slices in a different plane. This is commonly used to create sagittal and coronal images from the axial or transverse images. A maximum intensity projection, which is a MIP, which we just mentioned on the last slide, is the projection of voxels with the highest intensity onto an arbitrary plane. MIPs are commonly used in angiography with contrast or CTA exams to extract vascular structures from CT or MRI data sets. A radiologist will use a MIP to examine high attenuation in the pulmonary arteries to assess for any pulmonary emboli that are present. Minimum intensity projections, or MINIPs, it is when the projection of values with the lowest intensity into an arbitrary plane are projected. So here, the lowest data value encountered is recorded at each voxel. It allows for detection of low-density structures in a volume, so commonly used for rendering lungs and airway. So I just wanted to give you a few examples of an MPR, a MIP, and a MINIP. The picture on the left is an example of 3D rendering in multiplanar reconstruction. So you can see 3D right here. This is your axial or your transverse image. Bottom left is a picture of a sagittal image cut from the transverse image. And then also you have the coronal images as well. The image on the top right of your screen is an example of a MIP image. This is where you can see the high intensity in the pulmonary arteries. So for those of you who aren't familiar with CT, the pulmonary arteries will be bright when in a MIP image. So that just means that the contrast is being captured, which has the high intensity. This is a coronal MIP where a radiologist was looking for a PE. The bottom right image of your page is an example of a coronal manip in the lungs. You can see the lungs have very low intensity. As you can see, they're black. Radiologists also use lung manips to assess for ground glass opacities. So just a little bit more about surface rendering. Here's a great example. This is what it would look like. It treats the object inside a volume as having a surface of a uniform value, and images look like pictures of 3D solid objects.